All right, today we're diving into something really cool. It's a breakthrough in AI that's tackling some of the most difficult competitive problems you can imagine. We're talking about everything from generating hyper-realistic images to mastering super complex strategic games. We're going to break down a new research paper that found a way to solve a whole class of problems that have honestly stumped researchers for years. So let's jump right in. Okay, so let me start by asking you a question. On one hand, you've got these incredible generative AIs that can just dream up faces out of nowhere. I mean, they're so lifelike, you literally can't tell them apart from a real photo. And on the other hand, you have game-playing AIs that can outsmart the absolute best human champions in the world at games with mind-boggling complexity. So what's the connection? What's the hidden thread linking these two incredible feats? Well, the answer is that they're both what mathematicians call Minimax games. And this is a really special kind of problem where you have two AIs locked in a sort of digital duel. They have perfectly opposite goals. One AI is trying its hardest to maximize a score, while the other is simultaneously trying to minimize that exact same score. It's a high-stakes battle where every single move is a counter move. But here's the thing. Solving these games is incredibly hard. And to really get why, let's imagine the problem as a kind of playground for the AI. But it's a very, very tricky playground. It's bumpy, it's got boundaries, and it's the combination of the weird shape of the ground and the complex rules of the game that make it so tough. So let's really nail down what a Minimax problem is. Think of a game like tic-tac-toe. Player 1 wants to win, right? We can call that a score of +1. Player 2's goal is to stop Player 1 from winning, so their goal is a score of -1. Player 1 wants to maximize the score, Player 2 wants to minimize it. Every time Player 1 makes a move, Player 2 is thinking through all the possible counter moves to get the best possible outcome for themselves. It's this constant, back-and-forth, adversarial game that defines a Minimax problem. Now, a huge part of the difficulty comes down to what we can call the shape of the problem. As you can see here, simple optimization problems are convex. Just picture a smooth, simple bowl. If you put a marble anywhere in that bowl, it's just going to roll straight down to the single lowest point. Easy. But the AI games we're talking about, they are non-convex. Their world is much more like a rugged mountain range, full of countless peaks and valleys. An AI can easily get stuck in a small valley thinking it's found the lowest point when the true lowest point is a whole mountain range away. And as if that wasn't hard enough, this playground has rules. In math, we call them constraints. The best way to think about them is like fenced-off areas all over that mountain range. There are just certain places the AI players are forbidden to go. And that, of course, drastically limits their moves and makes finding a good strategy way more complicated. So you can see what happens. You combine that bumpy, unpredictable, non-convex landscape with a complex set of rules, these fenced-off areas, and you get a problem that has been a massive roadblock for AI research. And this isn't just some abstract puzzle. For years, this has literally stopped us from building more stable and more reliable AI systems. But that's exactly where this new research comes in. This is the big breakthrough. The authors found a new way, a new algorithm, that gives us a provable path forward for solving these exact kinds of problems. You see, the older methods, they just had some serious limitations. A lot of them basically had to pretend the problem was simpler than it really was, like assuming the mountain range was a smooth bowl, which we know isn't true in the real world. They just couldn't handle complex rules, and maybe most importantly, they came with zero guarantees. You could let an algorithm run for days and have no mathematical certainty that you were getting any closer to a real solution. And this quote from the paper itself really hits the nail on the head. When they say non-convex, non-concave, they're describing that double-sided challenge. It's a rugged landscape for both players. And then adding complex constraints on top of that, well, that's what made this whole class of problems so notoriously difficult to crack. So how did they pull it off? Well, their approach is this really smart three-step process. First, they reframe the game. They use a clever math trick to transform the original super hard problem into a different version that's actually easier to analyze. Second, they identify good areas. And this is the key insight. They use a special mathematical property. You can think of it as a tool that helps them find promising valleys in that mountain range, areas where they know they can make real progress and won't get stuck. Finally, they take a guaranteed step. Armed with that knowledge, their new algorithm takes a calculated step, and it does so with a mathematical guarantee that it's actually moving closer to a good solution. Okay, so a clever idea is one thing, but in science and math, you gotta prove it, right? You have to prove that it works and that it works efficiently. So let's talk about the proof of performance. I mean, it's a totally fair question to ask. How can we be so sure? How do we know this new algorithm won't just wander around that mountain range forever or get stuck in one of those little valleys just like all the old methods did? And the answer comes down to something called a complexity guarantee. Now, this isn't just a hopeful guess or something that worked a few times in an experiment. It is a rock-solid, rigorous mathematical proof. It promises that the algorithm will find a good solution in a predictable amount of time. It's not just a hope, it's a proven fact. And this right here is the headline. This is the big news. This research provides the first ever complexity guarantees for this entire class of non-convex, constrained Minimax problems. This is a huge deal. For years, this exact combination of a bumpy landscape and complex rules made it mathematically impossible to provide these kinds of guarantees. This paper breaks right through that barrier. It's like they've given us the first reliable map and a trustworthy vehicle to finally navigate that treacherous mountain range. So, we've talked a lot of theory. What does all this actually mean for the future of AI? Why does a theoretical breakthrough like this actually matter? Well, it's a really powerful tool for building better, more reliable AI systems across the board. Take those generative adversarial networks, the things that create fake faces. This method helps make their training game more stable, which leads to way more realistic images. For reinforcement learning, it means we can train AI agents to master more complex strategies, even in worlds with very strict rules. It also helps us build AI models that are provably tougher against attacks. And it even helps us design systems that work well when the data is messy or uncertain, which is, absolutely crucial for the real world. So, here's the crucial takeaway. This research gives us a key to unlock the next level of AI. It gives us a reliable way to train AI that's more powerful because it can handle these complex, realistic scenarios, and more trustworthy because for the first time, we have actual mathematical guarantees about how it's going to perform. And that really leaves us with one final thought to chew on. This research gives AI the power to find the best strategies in much more complex, rule-bound games. And as these digital playgrounds start to look more and more like our own complex world, from economics to global security, it really makes you wonder, who's going to write the rules for these games, and how do we make sure they're fair? Thanks for joining us for this explainer. All right, today we're going to dive into some really cool research that's basically teaching AI how to think like a master strategist. I want you to imagine two AIs locked in this high-stakes game of cat and mouse where every single move is a calculated risk. We're about to explore a brand new playbook that lets them play this game not in some sterile lab, but out here in the messy, rule-bound real world. So how do we even get our heads around this? Well, let's just frame it as a game, right? Picture two incredibly powerful AIs locked in a strategic battle where for one to win, the other has to lose. It's that simple. And this competitive idea, it's actually the heart and soul of some of the most advanced AI training that's happening anywhere today. So let's meet our players. First up, we've got the Forger AI. Its entire goal in life is to create fakes that are so convincing they're completely undetectable. It wants to minimize its chances of ever getting caught. And its opponent? That's the Detective AI. Its whole purpose is to get better and better at spotting those fakes, to maximize its own chances of winning the game. And this constant back and forth, this tug-of-war, has a name. It's called a Minimax problem. Think about it. Mini and max. It's a zero-sum game where the forger is trying to minimize the detective's score and the detective is trying to maximize its own. Now, this isn't just a fun thought experiment. This competitive dynamic is literally the mathematical engine that drives everything from game-playing AI to those systems that generate mind-blowing AI art. Okay, but this is where it gets really interesting. This is where the research we're looking at today takes a huge leap forward. We're about to add a whole new layer of complexity to this game, a layer that honestly mirrors the challenges of the real world perfectly. You see, that basic game between the forger and the detective, it's a great place to start, but it's just a little too clean, a little too simple. Real-world problems and the AIs that have to solve them don't get to operate in a vacuum. They have to follow rules. And these rules, or as mathematicians call them, constraints, are absolutely crucial. Think about it. An AI might have a limited budget. It only has so much computing power to work with. Or maybe it's running on a robot, so it has actual physical limitations. It might have to follow super strict safety protocols or be bound by data privacy laws that limit the information it can even look at. These aren't just little side notes. They're fundamental to making AI work safely and effectively out in the wild. So when you add these rules, you fundamentally change the game. It morphs into what's called a constrained nonconvex nonconcave problem. I know that is a total mouthful, but here's what it means. Imagine the AI is searching for the best move on a landscape. A simple problem is like a smooth bowl. There's one obvious low point to find. But this kind of problem, it's like a treacherous mountain range full of peaks, valleys, and dead ends. It becomes incredibly difficult to know if you've actually found the best solution or if you're just stuck in some random little valley. And here's the real kicker. For years, researchers have been really good at solving this simple version of this game, the one without any rules. But this more realistic, rule-bound version, the one where you have to navigate that treacherous mountain range, it's been a massive roadblock, seriously limiting what we can do with AI in the real world. Well, that is, until now. So the million-dollar question is, how did a team from the University of Minnesota create a completely new playbook to solve what was, for a long time, an unsolvable game? Okay, the paper calls its solution an inexact proximal gradient method, which sounds super complex, I get it. But the core idea behind it is actually beautiful in its simplicity. Instead of trying to find the one single, perfect, game-winning move all at once, which is pretty much impossible, they just break the problem down. They find a good enough direction to go in, and they do it by solving a bunch of smaller, way more manageable mini problems. Let's stick with that mountain climbing idea. Here's their 3-step plan. Instead of trying to map out the entire journey from the bottom of the mountain, first you reframe the problem. You just look at a simplified map. Then you solve a mini game to figure out the best way to get to the next campsite, a smaller, achievable goal. Finally, you update your position. You adjust your overall plan based on what you just learned, and then you do it all over again. They're breaking one giant, impossible climb into a series of achievable little steps. Now, you might be wondering, okay, but how do they know this step-by-step thing actually gets them to the top and not just lost? That's a great question. The secret is a really cool mathematical property called the local KL condition. In simple terms, this condition is like a guarantee that the landscape isn't too crazy. It promises that as long as you haven't found the solution yet, there's always a clear downhill path to follow. It's a mathematical safety net, ensuring their next campsite strategy always gets them closer to the real solution. So the strategy sounds pretty smart, right? But is it actually any better than what we had before? Let's take a look at the evidence because, honestly, the results are really impressive. This table just lays it all out. Look at where the old methods failed, handling real-world rules, navigating those tricky landscapes. This new method gets a check mark. But those last 2 rows, that's the real mic drop. It is guaranteed to find a solution, and it's provably efficient. That is a level of mathematical certainty that just didn't exist before in this space. The researchers nailed down what's called a complexity guarantee. You can think of it like a speed rating for an algorithm. It tells you how hard the algorithm has to work to get you a more and more precise answer. And this specific rating, which you read as big O of epsilon to the -2, is a huge deal. It's basically the gold standard for this type of problem, proving with cold, hard math that the method isn't just correct, it's also wicked fast. Okay, so we've been deep in the theory, but let's pull back. Why does any of this matter? Why should we care about this abstract game of forger versus detective? Well, because the real-world applications are poised to completely transform the field of AI as we know it. No, really, this isn't just theory. Each of these areas is its own high-stakes Minimax game. For AI art generators, what we call GANs, it's a forger AI battling a detective AI that judges how real the art looks. In cybersecurity, it's an attacker AI against a defender AI. For robots, it's an AI playing against the chaos of the physical world. By finally solving the constrained version of this game, we can train all of these systems to be way more stable, robust, and effective. The impact here is just sweeping. By finally cracking the code on these constrained, real-world problems, these researchers have given the entire AI community a new playbook, a way to handle not just the simple, abstract game, but the messy, complicated, and rule-bound challenges we actually need to solve. The mathematical engines that are powering AI are just getting more and more powerful all the time. This kind of breakthrough leaves us with a really fascinating final thought. What are the challenges that seem completely impossible to us today that will become just another complex game for the AIs of tomorrow to master? All right, welcome to The Explainer. Today we're diving into a really deep and fascinating challenge right at the heart of modern AI. How in the world do you train 2 competing AIs so they reach a perfect, stable balance? Well, it turns out some researchers at the University of Minnesota might have just found a brand new key. When we think about optimization, we usually picture a race to the top of a mountain, right? Finding that one single highest peak. But for a lot of the really advanced AIs we use today, it's not like that at all. It's much more like a high-stakes balancing act. I mean, think about an AI that generates realistic images and another AI that tries to spot the fakes. If one of them gets way too good, the whole system just collapses. It falls apart. Finding that perfect equilibrium, that stable point, that is one of the toughest nuts to crack in this entire field. So, how did they do it? Here's our game plan for today. First, we're going to unpack this AI tug-of-war. Then, we'll explore the incredibly treacherous digital landscape these systems have to navigate. After that, we'll talk about the mathematical compass they discovered to guide them. Then, we'll break down their totally new path forward. And finally, we'll get to the big one, why this all matters for the future of AI. Okay, let's get right into it. The heart of this whole thing is something called a Minimax problem. Now that sounds super technical, I know, but the core idea, it's actually way simpler than it sounds. It's really just a game of strategy. Just think about chess. You're trying to maximize your shot at winning, right? But at the same time, you're trying to minimize your opponent's chances. That's it. That's Minimax. And this exact same dynamic is what powers models like generative adversarial networks, or GANs. You've got one AI, the generator, acting like a master forger. Its only job is to create a picture of a cat that has never existed. And its opponent, the discriminator, is like the world's best art critic, trained to spot any tiny flaw that gives away the fake. They are locked in this constant, relentless game, and the only way they get better is by competing against each other. Now, while the idea of the game is pretty straightforward, the game board where this all happens is anything but. It is a seriously treacherous landscape, and it's defined by two really big mathematical challenges. It's nonconvex and it's constrained. Okay, first, nonconvex. What does that even mean? Well, an easy problem, a convex one, is like a perfectly smooth bowl. If you drop a marble in, it's going to roll right to the one single bottom. Easy. But a non-convex problem, that's not a bowl. It's an entire mountain range just filled with countless little valleys and false peaks. An algorithm can get stuck in one of those shallow valleys super easily, thinking it's found the best solution when the real lowest point is a whole mountain away. And then, as if that wasn't hard enough, you start adding rules. These are the constraints. Think of them like fences and no-go zones all over that mountain range. So now, the poor algorithm isn't just trying to find the lowest valley. It has to do it without breaking any of the rules, without touching any of the fences. It makes an already brutal journey exponentially harder. So, how do you navigate this insane, rule-bound landscape without getting completely lost? Well, this is where the magic happens. This is the real breakthrough. The researchers basically found a kind of mathematical compass to show them the way. It's called the Kurdyka-Łojasiewicz condition. Yeah, I know. Let's just call it the Kale condition for short. And honestly, don't worry about the name. Just think of it as a magic compass. It's a mathematical property that guarantees that no matter where you are, as long as you're not at the final answer, there is always a downhill path you can find. It stops you from getting stuck on some flat plateau, totally stranded. But here's the most brilliant part. This is the real genius of the paper. Before, old methods required this compass to work perfectly everywhere on the entire map. That's called a global condition, and it's incredibly restrictive, often impossible. What these researchers proved is that you only need the compass to work locally, just in the little neighborhood right around the solution. That is a much, much weaker requirement. It's like, instead of needing a map of the entire planet, you just need a map of the city you're in. It's so much more flexible, and it means their approach can be used on a huge number of real-world AI problems that were totally out of reach before. So having this key insight, this new local compass, allowed them to build a completely new path forward. It's a much smarter algorithm for finding that tricky balance point. So what does this new strategy actually look like? Well, you can think of it as this elegant little dance between the two AIs. First, the minimizing player makes a tentative move. Then its opponent, the maximizer, sees that move and calculates its absolute best countermove. After that, the first player looks at that countermove and takes a new, smarter step. And then they just repeat. This back and forth, guided by that local compass, lets them spiral in until they find that perfectly stable equilibrium. And make no mistake, this is a big deal. This isn't just some small improvement. As the researchers say themselves in the paper, they are charting entirely new territory. They say that before their work, there just wasn't a solid framework for handling these messy, rule-bound, constrained problems. They are the first to build a real solution based on this powerful local compass idea. So we've been deep in the weeds with some heavy math, I get it. But why does any of this matter? Well, because the real-world impact here is potentially huge. This could really affect the next wave of artificial intelligence. This new method could lead to some major breakthroughs. We're talking about GANs that are way more stable, that can generate hyper-realistic images and audio without just failing halfway through training. It could mean more robust reinforcement learning, robots that can actually learn complicated things in the real world. This also helps with security, making AI systems much harder to fool. It really all boils down to building models that are just more reliable, especially when they run into data they weren't expecting. Ultimately, what this research gives us is a powerful new tool for making sure our AI systems are stable and reliable, especially in a world where AI is getting more and more complex every single day. And that leaves us with one final big question. As AI keeps getting pushed to tackle these messy real-world problems with all their complicated rules, could this be it? Could this mathematical key be what finally unlocks the door to the next generation of truly robust and reliable AI systems?